Hi, welcome to Physics for Engineers. This is another video wherein we will tackle some of our example or sample problems. Let's go! For today, we will be having momentum and collision. So, let's have number one. Example number one. A ball of mass 0.150 kg is dropped from rest from a height of 1.25 meters. It rebounds from the floor to reach a height of 0.960 meters. What impulse was given to the ball by the floor? Okay, so this is our illustration for this problem. So we have here the before and then after dropping or after bouncing back. So before, it is coming from a height of 1.25 meters going down, and then after it rebounded into only 0.960 meters. So most probably there's been an effect from the floor, and that is the question: what is the impulse given by the ball to the by the floor? So for all we know, impulse is just equal to the force times the change in time, wherein impulse is also equivalent to the change in momentum. So our impulse now is just equal to P2 minus P1, or that is mv2 minus mv1. And for all we know that our ball is not changing them while it is gaining and decreasing momentum, our ball does not change its mass. So the mass is just the same. So momentum, not momentum, but the impulse now is this one. Impulse is just equal to mv2 minus mv1. But we don't know the speed v2 and v1. Or we don't know the velocity v2, v1. But it's very easy to get the speed. And that is just coming from the conservation of energy. All we know for this one, we know that we have an initial speed before it hits the ground. And then we have the speed after it hits the ground. And that's v2 for us. So we have to get v1 and v2. And focusing only here in our first motion, the going down the motion, we know that it is coming from the gravitational potential energy, it is being converted into kinetic energy. So energy. So you have u grav is just equal to k, or gravitational potential 1 is equal to kinetic 1. So we could get the speed v1, that is the square root of 2g y1. And then we have v2, the bounce back speed, and that is just coming from the initial or coming from the floor with an initial speed v2, and then it will rebound into, or it will bounce to the height that is 0.960 meters. That's the maximum height. So k2 is just, or k is just equal to gravitational potential energy, wherein y2 is just 0.960 meter. Hence we now have this equation again, wherein v2 is just equal to the square root of 2gy2, square root of 2gy2. Now, those are just speed. We need velocity because momentum is a velocity. Momentum is a vector, and getting momentum, we have to get also the velocity. It is a vector. So we know that before it hits the ground, it is going down. So v1 is going down and v2 is going up. So we have this convention now: v1 downward negative, v2 upward positive. So substituting our formula, this formula here with the negative and positive, we get this equation. That is our working equation. Substituting what we know, we now have this equation, this kind of long equation. It will give us a change in momentum, or an impulse of 1.39 kilograms meters per second. So that's for example number 1. Let's have example, you could take a screenshot if you want. Let's have example number 2. A 3 kilogram ball, a 3 kilogram steel ball, strikes a wall with a speed of 10 meters per second at an angle of 60 degrees. With the surface, it bounces off with the same speed and angle. If the ball is in contact with the wall for 0.200 seconds, what is the average force exerted by the wall on the ball? So I think I forgot to include the illustration for this one. So this is actually the illustrations of our example number 2, wherein initially it is coming at 60 degrees going to the wall, and it will bounce back at a certain angle also, and that is 60 degrees also with the same speed. So you have initial and final momentum. This is our initial 1, this is our final 2. And the same thing, we have impulse that is just equal to the change in momentum, where equivalent to force times delta t, wherein we are asked about the force, the average force. So we could have this one. So average force now is just equal to the change in momentum over the change in time, or delta t. And for all we know also that momentum has x and y components, and so is our forces. So it is right for us to get the magnitude. So meaning to say, f is just the magnitude of f is just equal to the square root of fx squared plus fy squared, wherein we have here f of x and f of y, or fx and fy. So fx is just equal to the change in momentum in x over change in time, and for fy, that's just change in momentum in y over the change in time. So we have to get them one by one. We have to decompose our velocity vector. So this is our velocity vector v1, and if this is 60 right here, this one here is also 60. And for this case, we know, I will stick with the 60 here. I know that the x component will just have the sine, I will use the sine function, and for the y component, we'll use the cosine function. And for the final speed or final velocity, we have here v2 right there. So we know also if that is 60 here, and this is 60 here. Well, if this is 60 here, this is also 60 right here, this angle. And for the x component, I know it is still using the sine function, and for the y component, it's still using the cosine function. So let's start with the x momentum. So you have mv2x minus mv1x, wherein the mass is still just the same. So you have v2x minus v1x. And we know that the final velocity v2, it is going here in that direction. So meaning to say it is going in the negative x direction. So I have here negative v2 sine 60, and for the v1x, that is minus v1 sine 60. So substituting all of our values, we get this one. So change in momentum px is just equal to negative 52.0 kilogram meters per second. And for py, we have this one. You have py1 and then py2. So that's mv2y minus mv1y. So we have here v2 cos 60 minus v1 cos 60. Well, cos 60, and then they will just be equal to 0 because they also have the same speed. So m now, or not the mass, the change in momentum along the y is just equal to 0. So meaning to say, all of our average velocity, or average force rather, will just be dependent on our change in momentum along the x. So that is, our average force now is just equal to the change in momentum in x over change in time. So that's negative 52 kilograms per meters per second minus 0.200 seconds. So the average force is negative 260 newtons. By the way, and this is very important also, I forget to write this one. This is along the x. Then if I'm going to get the magnitude f of, so that's the absolute value f of, magnitude lang ha, this is equal now to 260 newtons. Let's now have number 3. A 68.5 kilogram astronaut is doing a repair in space on an orbiting space station. She throws a 2.25 kilogram tool away from her at 3.20 meters per second relative to the space station. With what speed and in what direction will she begin to move? So we now have this one. I have these two scenarios here. I have the before and then after. As you can see, we are given here, let's look at the 3.20 meters per second. There's a keyword there relative to the space station. If, let's say for example, this is the space station, and uh, uh, that is the space station, and that's where the astronaut is. I will just denote wherein she will throw or he will throw the tool going to the right. Okay, and I will have that one as my positive x-axis. So relative to the space station, it's positive x-axis. So how can we get the speed and in what direction will she begin to move? This is actually very easy. This is from conservation of momentum only. We know that before she threw it or he threw it, their masses, the mass of the astronaut and the tool, is treated as one, and they are at rest. And then after throwing the tool will move. It will have a velocity, and then as well as with our astronaut, and they will be separated as he will throw the tool. So conservation of momentum, we treat this as one as the before throwing. We have one momentum, that is from the astronaut plus the tool, equal to after throwing, that is P astronaut 2 plus P astronaut 2. And we know that before throwing, it is they are both at rest, so the momentum is just equal to 0. So we are left with this equation. And we are after actually for the speed and direction of our astronaut after the throwing. So we got this working equation now. Substituting what we know, we will be getting negative 0.105 meters per second. Meaning to say, it is in the opposite direction relative to the tool. If the tool is going to the right, then the astronaut is going to the left with a speed of 0.105 meters per second. Okay, how do we know if that's kind of correct? Or if it's correct? Well, we just have to substitute this one to our equation, this equation. If this will equate to 0, then you are correct. And also, by theory, since the astronaut is massive compared to the tool, he or she will move slower compared to the tool. Hence, we have here a very slow speed. That's just 0.105 meters per second. Okay, so let's have number 4. This is kinda long, but it's very easy. A 20-kilogram body is moving through space in the positive direction of an x-axis with a speed of 200 meters per second. When, due to an internal explosion, it breaks into 3 pieces, or 3 parts. One part with a mass of 10 kilograms moves away from the direction of from the point of explosion with a speed of 100 meters per second in the positive y direction, moving up. A second part with a mass of 4 kilograms moves in the negative x direction with a speed of 500 meters per second. So that's that's going to the left. A. What is the velocity, magnitude, and direction of the third part? B. How much energy is released in the explosion? Ignore the effects of the gravitational force. Now, momentum is a vector. It has x and y and z components every one. So meaning to say, we could solve for the velocity of the third part just by using the idea of the conservation of momentum. But we have to understand this one first, conservation of mass. We have a body that's 20 kilograms, and then after explosions, it is being ripped apart into 3 pieces. You have the 4 kilograms, and then you have the 10 kilograms. By conservation of mass, we know that the third part, or the third piece, it is its mass is 6 kilograms. Okay, so I have this one, the before and then after collision. Now, initially, before explosion, not collision, explosion. Before explosion, it is a speed of 200 meters per second. And then after explosion, as we have seen here, we have the first part moving at 100 meters per second and the second one moving 500 meters per second. So how come it is this 500 is kind of questionable? How come it became 500 even though it's starting at 200 meters per second? For all we know, it is an internal explosion. There's that another kind of energy. wherein siya yung gumawa ng work. Someone or something done work to our different pieces. Hence, pwede siyang mag-speed up. Pwede din naman siya mag-slow down if it's doing negative na work. Okay? So, before and then after collision. We know that after explosion, after explosion, it's being ripped apart. We have motion sa X, motion in Y, and whatsoever. So we have to treat them as X and Y components also. So we have to rip them apart into X and Y also. So we now have this one. Momentum before is equal to momentum after. Before, mv1, after, mAv2, mbvv2, mcvc2. We are not sure if this is vc2 because we are after vc. We don't know that vc2 will it have y and x components, but we have to assume it has both x and y components. So let's start with the y component. So you have mv1y equal to mava2y plus mbvp2y plus mcvc2y. And then we substitute 0 equal to 10, 100 plus 0. y0 mbvb2y. Because it is purely in the moving in the x direction. So there's no y component. So that will become 0. Plus 6 times vc2y. We only have vc2y as our unknown. Hence, our vc2y is negative 167 meters per second. And for the x component, we now have this equation. And we know that initially it is moving in the x direction. Hence, we have 20 kilograms times 200 meters per second. MAVA2, well, obviously, VA2 is moving, or MA is going up. So there's no x component there. So plus 4 times negative 5 plus 6 VC2x. And then we only have VC2x as our unknown. So VC2x is just equal to 1000 meters per second. So for the magnitude, that's just the magnitude of VC is equal to the square root of VCx squared plus VCy squared, or this is actually 2 VC2. So we now have this one. We have 1014 meters per second. That's very fast actually. Well, it is as expected because there's an internal explosion. Okay? And for the direction, we have arctan Vy over Vx. It will give us negative 9.48. Well, by inspection, negative 9.48 is actually correct because our y component is negative while our x is positive. So it is belonging in the fourth quadrant. Negative 9.48 is acceptable. But I want it to become standard angle measurement. So I just added 360. So it's giving me 351 degrees. And that's for letter A. For letter B, the energy released by the internal explosion. So that's just the change in kinetic energy. The change in kinetic energy from before the explosion and after the explosion. So we have this equation. K2 minus K1, we now have this one. So substituting what we know, we'll get, well, since it is an explosion and it made our different pieces to speed up, we expect a positive value for this one. So we now have the energy released, we have positive 3.23 times 10 raised to 6 joules. That's for problem number 4. Let's have example number 5. Jack, with a mass of 55 kilograms, is sliding due east with speed 8 meters per second on the surface of a frozen pond. He collides with Jill with mass 48 kilograms, who is initially at rest. After the collision, Jack is traveling at 5 meters per second in a direction that is 35 degrees north of east. What is Jill's velocity, both magnitude and direction, after collision? So ignore friction. So initially, we have this illustration. You have Jack and Jill. Jack is only moving towards the east with a velocity of 8 meters per second. And I noted that east will be my positive x and my north, going north, is my positive y axis. So after collision, well, Jill is initially at rest. After collision, the speed of the Jack became 5 meters per second in the direction of 34 degrees. While Jill's velocity speed is cannot still be determined because we don't know any idea yet because we have to solve it first. So we have conservation of momentum. So momentum initial is equal to momentum final, wherein initially only Jack will have the momentum while Jill has zero momentum. Okay, and then after collision, the final momentum, both Jack and Jill will have a non-zero momentum. Meanwhile, for the x and y components, we're not sure if Jill has the x component only or y component. Hence, we have to assume that they are, or Jill is moving in the x and y. So let's start with the x component. So P1x is equal to P2x momentum along the x equal to momentum final along the x. So we have here our equation. And we know that Jill is at rest, so this will just become 0. Hence, we have this one. And we have to get the x component of Jack's momentum after collision. So this is our x component. It should have the we will be using the cosine function. So we now have this one. It will give us Jill's final velocity or final speed at 4.42 meters per second. Okay, that's along the x. And for the y-axis, we have this one. Initially, Jack and Jill will not have a moment. It will have a zero. They will have both zero momentum along the y-axis. So we only have the momentum final for the y-axis. So we have here 55 meters sine 34, and then we have 48 kilograms times the velocity or the velocity of Jill's velocity after collision. So we have here our final velocity after collision. This is for Jill. So we could now get the magnitude and direction. So for the magnitude, we will be using the idea of vectors Pythagorean relationship. So we now have 5.46 meters per second. And for the direction, we have the arctan. So we now have negative 35.9 degrees. And we know that Jill's x and y components lie in the fourth quadrant. So the negative 35.9 degrees is acceptable. But I want it to be standard, so I will add 360. So it will give me 324 degrees. Let's have example number 6. A 5-gram bullet is fired horizontally into a 1.20 kg wooden block resting on a horizontal surface. The coefficient of kinetic friction between block and surface is 0.20. The bullet remains embedded in the block, which is observed to slide 0.310 meters along the surface before stopping. What was the initial speed of the bullet? So we have to get the initial speed of the bullet before it becomes embedded in our block. So I want to focus first on this one, because before I could get the initial velocity or initial speed of the bullet, I should know first, after embedding, what would be its speed after embedding, after the collision between our bullet and of our block. So with that, let's have the second scenario, wherein after collision, the block and the bullet is being embedded on the block. It will move 0.310 meters before stopping. While with friction, friction is acting with a coefficient of 0.20. Now, we have to get this one, the moment that it will the moment that the bullet will embed itself to the block. So this one, we have to get first this speed, okay, or velocity if you want. So solving for that one, I have to analyze this one. This is my initial and this is my final. I want to analyze them using energy, conservation of energy, because I have friction. There's someone that's doing work against our motion. So we now have this one. KAB1, we only have kinetic energy and we don't have any potential energy, plus work done by other forces, which is of friction, equal to 0. Why? Because it will eventually stop. There's no kinetic energy anymore. Meaning to say, all of my kinetic energy is being counteracted by our work done by friction. Okay, so this is the standard operating procedure. Work others is work done by friction. So wherein I have to get the work done by friction, and that is Fs cos phi. Well, we don't have F because that's the force acted by our friction. That's equal to mu k Fn, mu times the normal force. And then the normal force is just equivalent to the weight for this case, because using summation of forces or Newton's second law of motion, we could get that one, wherein the force or the normal force is just equal to the weight. So now, the work done by friction is equal to mu mgs cosine theta. Substituting that one to our original equation, we could now have this, wherein we could further simplify that one. We now have this one, and then we now have this one, that equation. And then after that, we could get the speed of our block after collision, and that is 1.10 meters per second. And then after that one, we could get now the initial speed of our bullet. And we will go back to this scenario using momentum. Okay, wherein I have to write this one. I will analyze it from here to here, the moment that it will embed itself. So we now have this one. P1 equal to P2 is equal to PA1 plus PB1. The initial momentum of the bullet, of the block, and then the final momentum of the bullet and block embedded together or moving together. So we now have this working equation, wherein this m prime that pertains to the mass of the block and the bullet together and moving as one. And initially our block is has zero momentum, so this will become zero. So we only have this equation, giving us the final speed of our bullet, or not the final speed, the initial speed of our bullet, that is 265 meters per second. So that's for example number 6. Coming from this one, we have to separate this analysis and then we move to that one. Okay, so we now have this answer, that 265 meters per second. Okay, so let's have number 7. Number 7 is kind of different. This is elastic collision. Two titanium spheres approach each other head-on with the same speed and collide elastically. After the collision, one of the spheres, whose mass is 300 grams, remains at rest. The collision is elastic. Ulit. What is the mass of the other sphere, and what is the speed of the two sphere center of mass if the initial speed of each sphere is 2 meters per second? Okay, so we have first to get the mass of the other sphere. Now this is an elastic collision. Elastic collision will have a very long very long equations for that one, very long solutions. But we could simplify it further, wherein we could have this summary of equations. This pertains to the final velocities of our block or of our moving objects, two moving objects. Okay, so we just have to know the initial velocity of the two objects and then their masses, ma, mb. Now let's have this one. So this is before collision. We have two spheres. I will denote this one on the right, as my mb with a mass of 300 grams, wherein that's 300 times 10 raised to negative 3 kilograms, and ma as my unknown mass. Okay, and then after collision, the mass mb becomes at rest, that's moving, so fb2x becomes 0, wherein we don't know mass ma. Okay, so we could now get that one. So just take note, the initial magnitude of our spheres are the same. They will just have the same speed, so let's have that as v1. And then va1 is just equal to v1x, vb1x is just equal to the negative of v1x. Why negative? Because it is moving on the opposite direction. They are colliding head-on. Okay, so I will be using this equation. Just take note that vb2x after collision is 0. Hence vb2x 0. We now have this one. We will use this equation. So we now have vb2x is equal to 2ma over ma plus mb times v1x plus mb minus ma over ma plus mb times vb1x. Note that vb2x is 0. And we already know v1x and va1x and vb1x. They're just v1x and the other one is v1x because they are moving at the same speed but opposite direction. Further simplifying this equation, we could now have this one here. And then further simplification, 1 over v1x, we could have this equation, giving us now ma, the mass of the unknown object, 300 grams over 3. It gives us 100 grams, or that's 100 times 10 raised to negative 3 kilograms. So that's now for letter A. That's our MA. Let's have letter B. What is the speed of the two-sphere center of mass, the center of mass of our two moving objects, if the initial speed of each sphere is 2 meters per second? So we now have different ways in getting for the center of mass. For this case, we will be using the momentum. So we will now have this one, and the mass total times the velocity of the center of mass equal to the individual masses, the moment of individual masses, ma va1x plus mb vb1x. We are after this one. What is the speed of the two-sphere center of mass? So VCM now, it will give us, since this is just speed, magnitude will give us 1 meters per second. That's how we go about letter B. Let's have example 8. This is actually similar to the previous example, wherein we will be using energy also. So, a steel ball of mass 0.500 kilograms is fastened to a cord that is 70 cm long rather, and fixed at the far end. The ball is then released when the cord is horizontal. At the bottom of its path, the ball strikes a 2.50 kg steel block, initially at rest on a frictionless surface. Find the collision. The collision is elastic. Find A, the speed of the ball, and the speed of the block, both just after the collision. Speed of the ball and block after collision. So, initial velocity, I have to get first the initial velocity. This is my illustration actually. I have to get the initial velocity before the collision, the initial velocity of my mass ma, or of that ball. And through conservation of energy, I could get that one. So I could have here u grav is equal to kinetic energy, as seen here, wherein this is our reference point 0, and then coming from here, it will go down, so that gravitational potential energy will become kinetic energy. So we now have u grav is equal to k, giving us now speed that is equal to 3.70 meters per second. That's the speed of our ball before collision. Now, we have to get the speed of the ball and the block after collision. So, we now have this kind of illustration. So, this is before collision, and then what will happen is, this is our after collision. We don't know where they are going afterwards, after collision. And since this is elastic collision, we can make use of our two equations. We already know the initial speed of our block and of our ball, so we could easily solve this one. And since before collision, VB1 is equal to 0, wherein the block is not moving, so we could get the speed of our ball after collision using this one. Okay, so it will give us negative 2.47 meters per second. Negative because it is going on towards the opposite direction of relative to the block after collision, but we're just after the speed, so magnitude will give us 2.47 meters per second. And for the block, the speed of the block, we will be making use of that one. So since VB1 is 0, so we're left with this one. So with that, we could get 1.23 meters per second. Positive because it is going to the right of our motion, or to the right relative or opposite relative to our ball. So that's how we get this example number 8. By the way, it's kinda easy. Let's have number 9. Yeah. Example number 9. So we now have this one. A 1,200 kilogram SUV is moving along a straight highway at 12 meters per second. Another car with mass 1,800 kilogram and speed 20 meters per second has its center of mass at 40 meters ahead of the center of mass of the SUV. Find A, the position of the center of mass of the system consisting of the two cars. B, the magnitude of the system's total momentum by using the given data. C, the speed of the system's center of mass. D, the system's total momentum by using the speed of the center of mass, and compare our results with part B. We now have this simple illustration wherein we could have MA and MB already. So we have the 40. By the way, for letter A, I want to get the position of the center of mass of the system. And then it's not easy as dividing 40 meters, okay? So I want to make use this one, this right here, as my reference point. Meaning to say, I will be getting the center of mass with respect to here. Okay, so with that, I will be using this equation. Okay, the center of mass equation, where I have to get this one. The mass of the total the mass total of our system is MA plus MB. So we now have this one. Substituting all of our values, giving us now the center of mass, the position of our center of mass, and that is 24 meters. That is with respect to the reference point. Coming from the left, going 24 meters. That's the center of mass of our system. Okay? And then for letter B, the magnitude of the system's total momentum. So for the total momentum, let us just we add all the momentum. We add the momentum of car A, or momentum of the 1,200 kilogram car, and the momentum of the 1,800 kilogram car. It will give us 50,400 kilogram meters per second. And that's the total momentum. And for letter C, the speed of the system's center of mass. So we now go to the idea of the center of mass using momentum. So we now have this one. We are after this, we have to get this one. So we divide both sides by, we have to multiply both sides by 1 over mt. So we now have this 1. Substituting everything, it will give us the speed of our center of mass, 16.8 meters per second. And lastly, for letter D, the total momentum, but using the center of mass, the speed of the center of mass. So that is mt VCM. So that's 1,200 plus 1,800 times 16.8. It will give us 50,400 kilogram meters per second. So our answer for letter D is actually the same with our answer for letter B. Okay, why? Because this center of mass is actually, it is acting na we get the average of all the masses wherein they are located at that one point, wherein it will converge at that point. Okay, so meaning to say, the momentum of our center of mass is actually equivalent also to the momentum of our total momentum for MA and MB, or of PA and PB. Hence, they are just the same. So that's for example number 9. So I will leave you with this one. You could take a screenshot of all the of all the solutions. So let's start with this one. And just you could take a screenshot of this one. This one, 1, 2, 3. This one, this page. There. This one. There. This. This one. And lastly, number 9. Okay? So that's for our example.